Hello and welcome back to Manifolds, the video series where we talk about integration on generalized surfaces. And in today's part 52, we will finally start talking about the famous theorem of Stokes. This one is often called the Generalized Stokes theorem because it's formulated on abstract manifolds with boundary. However, before we formulate Stokes' theorem, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that as a member on Steady or Patreon, you can download a lot of additional material for the videos. This might be quite helpful for learning because you can access the PDF versions and the quizzes for the topics of today. And now I would say, in order to get an overview of Stokes' theorem, let's first look at classical vector analysis. There, one usually considers a two-dimensional surface in a three-dimensional space. And in this picture you can see we have a manifold boundary for this surface. And you might know, exactly for this case, we have the classical theorem of Stokes. It's also called the curl theorem because it's about the curl of a vector field. So without going into the details, you just have an integral over m of the curl of a vector field, and this one can be reduced to an integral over the boundary of m. Roughly speaking, that's already it, but I omit some details about the nature of these integrals. And also you might remember that we have an orientation on the boundary which is important. But by filling in the details, what you get is the classical version of Stokes' theorem. And in the case that you know that, it's also likely that you know Gauss's theorem as well. And this one is definitely often known as the divergence theorem. Simply because now in the integral on the left hand side, we have the divergence of the vector field rather than the curl. And moreover, often Gauss's theorem is formulated for three-dimensional manifolds. In that case, the boundary of this manifold is a two-dimensional surface in the space again. Hence, in this example, the sphere as a surface would be our del M. And on the other hand, the full ball is our three-dimensional manifold with boundary. And now the divergence theorem, Gauss's theorem, tells us that we can reduce this integral over the divergence of a vector field into an integral over the two-dimensional surface del M. Also here I skip some details of these integrals. For example, there's also an orientation of this surface involved. However, in this short formulation here, you immediately see that the two theorems here are definitely similar. And now if you recall that the curl and the divergence can be expressed with our exterior derivative, you immediately see the generalized version of the theorem. In other words, these two results here are just two special versions of the generalized Stokes theorem. And usually also this generalized version on abstract manifolds is also just called Stokes' theorem in short. And now I would say, let's immediately formulate this important theorem for abstract manifolds with boundary. Which simply means in a generalized version we can still use the picture from above. The only difference is now that M is a general n-dimensional manifold. And in addition, as you already know, it's a manifold with boundary and it also has an orientation. Therefore, we have an induced orientation on the boundary del M as well. So you can say it simply inherits a positive orientation from M. So this is one ingredient we need, and another one is a differential form on M. More precisely, it has to be an n-1 form because it should be a volume form on the boundary. And now it's quite important that this volume form omega does not stretch to infinity, so we need to have compact support. So if you don't know what it means, I can quickly write down the definition of the support of a differential form. Roughly speaking, the support just considers the points where the form does not vanish. So you have the set of all p in M with the condition that the form omega p is not the zero form. And now it could happen that this set is actually not closed in M, but we want to force it. We want that the support is always closed. So we just go to the closure, and this is what we call the support of omega. And now this is the requirement we have. This set should be a compact set. And now the conclusion here is that we have the formula of Stokes' theorem. So instead of integrating the volume form d omega over m, we can also integrate the form omega over del m. So I really think this formula is quite easy to remember because there's always a d involved, either at the form or at the manifold. And therefore now you know Stokes' theorem reduces the integral from an integral over the whole manifold to an integral on the boundary. And by looking at the special versions we had before, you already know that this theorem is quite important in applications. Therefore, before we talk about the proof, I first want to show you some direct applications of the theorem. And to make the requirements simpler, we can assume that our manifold M is compact. Indeed, this is what we often have, and it also means that the compact support is satisfied for every differential form on the manifold as well. And now what we could consider is a manifold without a boundary, so a standard smooth manifold where the boundary is empty. Then Stokes' theorem is still applicable, but the right hand side here is just 0. Which immediately implies that integrating any differential form d omega gives us 0. Obviously this is quite interesting because it's a general result for manifolds without a boundary. On the other hand, we could also consider manifolds with boundary, but then we could look at differential forms where d omega is equal to 0. Hence then in Stokes' theorem the left hand side vanishes. So the conclusion is that integrating omega over the whole boundary still vanishes. Here we see we get the value of an integral without even calculating the integral at all. And in fact this result can also be used if the boundary splits up into two parts. A typical example of that would be a tube with two exits. Then in that case we know that Stokes' theorem only says something about the integral over the whole boundary. Hence if we call the one part of the boundary n1 and the other one n2, then it does not tell us what the integral over n1 is. But it definitely tells us that the two integrals are related. Namely, if you know one, you also know the other one. The only thing that changes is the sign, because both things together should be equal to 0. So this is also a general result that can be used in explicit examples. And obviously, a simple example would be the one-dimensional case. So I just want that M is a compact one-dimensional manifold with boundary embedded in Rn. And to avoid some confusion, let's say we have Rd. So the manifold M is not so special, it's just a curve in Rd. And in order to keep it interesting, let's say that we have two different endpoints. So we have P0 and P1, and there should not be the same points in Rd. So really not complicated, and now we can say that we have a parameterization phi. And this one should have the domain given by the interval a to b. So this means that we extend phi to the boundary points such that phi of a is equal to p0. And on the other side, p1 should be given by phi of b. So you see, we don't have a problem at all, and we can apply Stokes' theorem where the boundary points are just given by 2 points. And as we have discussed in former videos, even in this zero-dimensional case, we have an inherited orientation. Therefore, two different signs are involved, and we also assume that phi is an orientation-preserving parameterization. And now you know for applying Stokes' theorem, we have to consider a zero form in this case, which we can simply express as a smooth map f on the manifold M. So let's simply use Stokes' theorem, which means we have an integral over f and 1 over df. And then on the left hand side we only have the boundary, and on the right hand side the whole manifold M. And I use this order because the left hand side is quite simple. It's just an integral over 2 points where we have two signs involved for the orientation. This property we have already discussed in part 48, and it results in f of p1 minus f of p0. So there we have it. This is the left hand side of Stokes' theorem, and now we can go to the right hand side. And there we can use our parameterization phi, which means M is given as the image of the interval AB under phi. And by using the open interval here, we omit the boundary points, but it means we actually describe an ordinary smooth manifold. Therefore, we can just use everything we know about the abstract integration on manifolds. So for example, here if you want, we can use the change of variables formula, which means now we just integrate over the one-dimensional manifold given by the interval. And moreover, we also have the natural property of the exterior derivative, which means we can pull in the star operation. However, there you know the pullback of a smooth function is quite simple because it's just given by the composition. So you see what we have to integrate here is simply df after phi. However, this one is just an ordinary function from r into r, so this differential here is just given by the ordinary derivative. Which also means that we can just leave the abstract integration here and go to our concrete one-dimensional integration. Therefore, we can also finally write the integral from a to b here. And then as already mentioned, we have the ordinary derivative here, and let's say it's at a point t. And at this point you could say we don't have to deal with manifolds anymore, because we could see f as a map from Rd into R. So by having such a natural extension of f, we can use the standard chain rule here. So in general, this means we have the composition of two Jacobians, but in this case here, we can reduce it to the gradient of f and the standard derivative of phi. Moreover, the product of the two Jacobians means we have to look at the standard inner product of these two vectors. So on the one hand, gradient of f at phi of t, and on the other hand, phi prime of t. So this goes together and we still integrate over t. And there we have it. This is the general result which we get for such a curve in Rd. On the left hand side we have something we could call a potential difference, and on the right we have an integral over the gradient inside the standard inner product. In particular, this result tells us that changing the parameterization will not change this integral on the right hand side. So this was already a very explicit formula that comes out of Stokes' theorem, and therefore I would say in the next videos we tackle the proof of it. Therefore I really hope that we meet in the next video again, and have a nice day. Bye bye.